Next question involves a 4 cubic millimeter volume being expelled from the pressure inside some body of water to the outside where the pressure is equal to the atmospheric pressure. Okay, so that's the kind of situation we're talking about. Now, didn't tell you anything about the dimensions of this thing, only that it has a volume of 4 cubic millimeters. So I asked for possible dimensions. And we got, well, 2 by 2 by 1, meaning 2 millimeters by 2 millimeters by 1 millimeter. 1 by 2 by 2, 4 by 1 by 1. 2, if we go length, width, height, then length of 2, depth of 2, height of 1, the increment could look like this. If it's 1 by 2 by 2, length 1, depth 2, height 2, width 2, you understand what I'm saying, or 4 by 1 by 1 would look like this. So we could have any of these shapes. Let's just choose the last of the shapes and do the calculation. We have a 0.110 newtons per square millimeter inside and a 0.100 newtons per square millimeter on the outside. So that this, whichever of these shapes is here, it's got the 0.110 newtons per cubic millimeter here. And we'll erase this. This indicates, of course, that the thing is being expelled with some velocity, and a somewhat smaller force on this side, which is going to accelerate the object out of the container and with some velocity. Okay, well, it's very straightforward to calculate the forces. We're going to get 0.110 newtons on this shape because, of course, each end is 1 millimeter by 1 millimeter. It's a square millimeter. And at 0.110 newtons per square millimeter, that's 0.110 newtons is exactly what we're going to get on a square millimeter. Similarly, we got 0.110 newtons over here. So we have a net force of 0.010 newtons. And this is going to be accelerated through a distance of 4 millimeters in the direction of the net force, so that the work done is going to be 0.04 Newton millimeters. Now, that's if we have this shape. What if we have, say, this shape? Well, then we're going to have 2 square millimeters on each end. So we're going to have double the forces, which is going to give us double the net force. Isn't that going to give us twice the work? Well, no, because this thing is only 2 millimeters long as opposed to the 4 here. So it's got twice the force, but it's only half as long, so we go through only half the distance. So this is going to experience twice the force, but it's only going to be exerted through half the distance, meaning that the work is going to be identical. And in this case, you can verify that you're going to have 4 square millimeters on each of these faces. So you're going to have 4 times the net force, but you're only going through 1 millimeter. You're going to have 4 times the force through 1/4 of the distance. You're still going to end up with 0.04 Newton millimeters. Now, you can prove, if you do this symbolically, and I've asked you to do that, and Richard came up with some good ideas, which hopefully everybody picked up on. You can prove that whatever 4 cubic millimeter volume you have here, as long as the thing doesn't extend very far in the vertical direction, which would give a significant difference in pressure, you're going to get the same result. Now, I say that the work done then is equal to the negative of the pressure difference times the volume increment. So I'm replacing the 4 cubic millimeters with a delta V and a delta P, which of course corresponds to our 0.01 Newton per square millimeter difference. So we have a delta P, and I say it's negative 0.01 Newton millimeter squared because the pressure is going from higher to lower. The pressure is decreasing in the direction of motion. The volume increment, 4 millimeters squared, so for this case, the negative delta P times delta V is going to be 0.04 Newton millimeters. Okay, so if we multiply this by this, we get 0.04 Newton millimeters.